Hello everyone, my name is Hunor and today we are going to cover how to code Crossy Road again. We already covered this game with three.js and vanilla JavaScript, so let's see how to make the same game with React Tree Fiber. Of course, React Tree Fiber also uses three.js under the hood, but it gives us a different way to build up our game with React. And if you haven't watched the previous video, don't worry, we are going to cover everything from the start. The goal in this game is to move a character through an endless path of static and moving obstacles. We have to go around the trees and avoid getting hit by a car or a truck. We start with the basic setup. We are setting up the scene, the camera, and the lights. We learn how to draw the player and the map with the trees and the cars and the trucks. We cover how to animate the vehicles, and we add event handlers to move the player through the map. Finally, we add hit detection to detect if there's a collision between the player and the car. There's a lot to cover, so let's get started. First, let's set up the drawing canvas, the camera, the lights, and let's render a box. That will be our player. To initialize the project, I recommend using Vite. With Vite, you can just go to your terminal and type npm create Vite to initialize a project. Then select React as a framework. React Tree Fiber is using React. In this tutorial, we go through the code in TypeScript. In the previous tutorial, we used JavaScript, so let's step up our game and use TypeScript this time. If you are not familiar with TypeScript, then you can just ignore the types in the code. After initializing the project, let's navigate to the project folder and install the additional dependencies. We are going to use three.js, React Tree Fiber, Dry, and Zustand. Now let's have a quick note on the versions. At the time of recording, by default, Vite will use React 18. This is actually good because it's compatible with the latest stable version of React Tree Fiber. At the moment, if you are using React 19, you need to install the release candidate version of React Tree Fiber. Of course, if you're watching this video in the future, then Vite might have switched to React 19 already, and hopefully by that time, version 9 of React Tree Fiber is out already. From the perspective of this tutorial, it doesn't really matter which version you're using. There's only one minor difference between the two versions, and there I will show you the code for both. Now that you set up the initial project, you can start a development server with npm run dev, so you can follow the result of your coding in the browser. Let's create a new file for our game component. This component will be the root of our game. In this component, we have the scene component that will contain the drawing canvas, the camera, and the lights. And we pass on the player component as a child, which will render a box. Later, we also add the map component here that will include the trees, the cars, and the trucks. This component will also include the score indicator, the controls, and the result screen. To use our new game component as our root component, we need to replace the original app component in the main file. This will give you an error for now because we haven't defined the scene and the player components. We are going to define them in the next steps. Before we get there though, let's just clean up this project. We can remove the original app component with its styling, and we can remove the assets folder. We can also get rid of most things in the CSS file. All we need for now is that the body and the root element is filling the whole screen. Now let's look into the different camera and light options. There are two main camera options, the perspective camera and the orthographic camera. The perspective camera is the default camera in three.js, and it's the most common camera type in video games. It creates a perspective projection, which means that things further away from the camera appear to be smaller, and things right in front of the camera appear to be bigger. The orthographic camera creates parallel projections, which means that objects have the same size regardless of their distance from the camera. We are going to use an orthographic camera because it gives our game a more arcade, retro, boxy look. Now let's talk about the coordinate system, the camera position, and the camera direction. We use a coordinate system in which the ground is the xy plane and the z-axis is pointing upwards. This way, the player can move left and right along the x-axis, forward and backward along the y-axis, and when the player is jumping, it goes up along the z-axis. We are going to position every 3D object in the scene along the x, y, and z-axis. We place the camera on the right along the x-axis, behind the player along the y-axis, and above the ground. The camera then will look back at the origin of the coordinate system, at the 0, 0, 0 coordinate, where the player will be initially. Before we define the camera for our scene, let's talk about the different light options. There are many different light options in three.js. We are going to use an ambient light and a directional light. The ambient light brightens the entire scene. It doesn't have a specific position or direction. You can think of it as the light on a cloudy day when it's bright but there are no shadows. The ambient light is used to simulate indirect light. The downside of using an ambient light is that as a result, every side of our objects are equally bright. Every side of our boxes have the same color, so we don't see the edges of the box. A directional light has a position and a target. The position is a bit misleading here though. It doesn't shine from one point in every direction like a point light. The position and the target are used to set its direction. You can think of it as the sun, which is shining from very far away, and the light rays are parallel. The directional light can also cast shadows. We are going to use that. The downside of a directional light is that sides of the objects that don't receive light directly are completely black. That's why we are going to combine the two lights. The ambient light will give the whole scene a base brightness, and the directional light will highlight some sides of the shapes. So after reviewing the different camera and light options, let's put them together in the scene component. We set up the canvas with an orthographic camera and the lights. Here we use the canvas component from React Tree Fiber. This component will contain every 3D object on the scene, so it has a children prop. To use an orthographic camera, we set the orthographic prop to true. Then we also set the camera's position and orientation. We set the camera position along the x, y, and z axis. We move it to the right along the x-axis by 300 units, before the player along the y-axis with minus 300 units, and above the ground with 300 units. The up property sets which way is upwards. Here we set the vector in a way that the z-axis is pointing upwards. Then we add the lights. We can add React Tree Fiber specific elements to the canvas element. Here the ambient light and directional light are not HTML elements and they are not components that we are importing either. But because we are inside a canvas element, React Tree Fiber knows that these represent an ambient light from three.js and a directional light from three.js, so it will render it accordingly. We also position the directional light to be to the left from the player, behind the player, and above the ground. Now that we defined the scene component, let's also define the player. In the game component, we already passed the player component as a child to the scene. Initially, the player will be a simple box. To draw a 3D box, we define a geometry and the material. The geometry defines the object's shape, and the material defines its appearance. Here we use box geometry to define the box. The box geometry takes three arguments: the width, the depth, and the height of the box along the x, y, and z axis. There are different types of materials in three.js. The main difference between them is how do they react to light. We use a mesh Lambert material, a simple material that is responding to light. We set the color prop here to white with a hexadecimal value. We've wrapped the geometry and the material into a mesh. A mesh is an object that we can add to the scene. We can also position a mesh. We set the box position with the X, Y, and Z positions. In the case of a box, these set the center position. Here we elevate the player above the ground by half of its size, and as a result, the bottom of the box will be on the ground. So basically the player is standing on the ground. Now let's talk about framing the scene. If we have a shape that's facing the camera and we use an orthographic camera, then one unit in the scene is matching 1 pixel on the screen. This will be even true if we resize the screen. If we enlarge the browser window, the size of the objects within the canvas don't change. Instead, the camera will expose more of the scene. This is not what we want. We want to show the same content regardless of the screen size, the close surrounding of the player. So let's change the code to achieve that. We frame the scene using the bounce component from Dry. The Dry package is a collection of utility functions from which we are only going to use the bounce component. This calculates the boundary box and frames the scene according to the margin prop. We want to frame the player, so we wrap it in the bounce component. This component calculates the size of its children, this time the player, then multiplies the size by the margin prop, and that will be the size of the visible area. If the margin is 1, the child component fills the entire screen while keeping their proportion. If the margin is, let's say, 1.2, then there's a 20% margin around them. If the margin is 10, like in our case, the visible area is 10 times the size of the child components. The bounce component also sets the camera target to look at the center of this bounding box. In this case, it's going to look at the center of the player. Now that we can render the player, let's move on and render the map. The map will consist of multiple rows, each described by a metadata. Each row can be a forest, a car, or a truck lane. We will go through each type and define the 3D objects that represent them. If you are following along with TypeScript, then let's create a new file for defining the types. Here we're going to have a row type, which is a union of the different row types. And the row type is a union of the different row objects. Here we have the description for the forest row, for the car lane, and the truck lane. We are going to go through each type as we are implementing them. Each row also consists of multiple tiles. The player will move from tile to tile. The trees are also placed on a tile. Cars and trucks, however, do not relate to tiles because they are moving freely through the lane. Let's also define another file with the constant values. In this file, we define how many tiles each row has. In this case, we say that we have 17 tiles, which are going from -8 to +8. The player will start in the middle at 0. Now let's start building up our map, and let's define our initial row. Let's create a new component called map. This component will contain all the 3D objects for every row. For now, let's add a single grass component as the starting row. To the grass component, we pass on the row index. The grass component will position itself based on this index. The first row is row 0, but as we are going to have more rows, we're going to have row 1, row 2, and so on. We are going to extend this component with all the other rows, so let's wrap the returned component into a fragment. Now let's define the grass component. The grass component is the foundation and container of the forest rows, and it is also used for the starting row. Its content is a flat, wide green box. The dimensions of this box are determined by the constants tile size and tiles per row. It also has a bit of a height, so it sticks out compared to the road component, which will be completely flat. The grass component also serves as a container for the trees in the row. The forest component will pass on the trees as children. So we wrap the green box and the children into a group element. The group element is a container that can hold multiple 3D elements and apply transformations to all of them at once. We position it along the y-axis based on the row index. This way, each row will have a different position. Now that we defined our map component that includes a single grass component for now, let's add the map component to the scene in the game component. This will render the starting row. Now let's add more rows to the map. Let's extend our map with a forest row. We define metadata for the map and render the rows based on this data. Let's create a new file for the metadata. The metadata is an array of objects that contain information about each row. Each row object contains a type property that sets if you have a forest row, a car, or a truck lane. The rest of the properties depend on the row type. For now, let's hardcode the values for one single row. Later, we are going to generate rows dynamically. The metadata for the forest row has type forest and a list of trees. Each tree has the following properties. The tile index sets on which tile the tree will stand within the row. In this case, the tile index is ranging from -8 to +8. Then we also have a height property that will set the height of the crown of the tree. Now to render this metadata, let's extend the map component. We import the metadata and we map each row to a separate row component, which we haven't defined yet. Note here that the row index is off by 1 compared to the array index, because the first item in the metadata will become the second row, after the starting row. Now let's define the row component. The row component is essentially a switch case that renders the correct row based on the row type. For now, we only support the forest row type, but we will extend this file later to support car and truck lanes. We have a lot of boilerplate at this point, but as we are going to extend, it will all make sense in the end. Then the forest component contains the row's foundation, a grass component, and the trees in the row. We define the grass component in a way that it can receive children. So here we map the tree's metadata to tree components and pass them on as children to the grass component. Each tree will receive its tile index, which will be used to position the tree within the row, and its height. Now let's see how to render a tree. We build up a tree from a trunk and a crown. Both are simple boxes, just like we used for the player and for the grass component. The trunk is placed on top of the ground, we lift it along the z-axis by half of its height, and the crown is placed on top of the trunk. The crown's height is based on the height property. Then we wrap these two meshes together with a group element and position it along the x-axis based on the tile index. With this, a forest should show up on the screen. Now let's add support for car lanes. We define the metadata for the vehicles and map them to 3D objects. So let's replace the forest row in the metadata to a car lane. The car lane will contain a single red car moving to the left. Each car lane object will have the following properties. They all have a direction, which is a Boolean flag that sets the direction of the vehicles. True means that the cars are going to the right, and false means that the cars are going to the left. We also have a speed property that tells us how many units each vehicle takes in 1 second. And then finally, we have a vehicles array that is an array of objects containing the metadata for each vehicle in the lane. Each vehicle will have an initial tile index, which only defines the initial position as the vehicles are going to move after that, and they have a color. Now let's extend the row component with support for car lanes. If the type of a row is car, we map it to a car lane component. Then the car lane component renders the cars on the road. It has a similar structure as the forest component. It receives a road data object as a prop which contains the cars to be rendered. It wraps the cars in a road component and maps over the vehicles array to render each car. Now the road and the car components are new here, so let's define them. The road component is the foundation and container for the car and truck lanes. It contains a gray plane. Similar to the grass component, its size is also calculated by the constants tile size and tiles per row. Unlike the grass component though, it doesn't have any height. The road component also serves as a container for the cars on the road. It has a children prop. The car lane and the truck lane components pass in the vehicles as children. Now let's define the car component, which will return a simplified 3D model of a car. It consists of a box that is the body and a smaller box on top of it, and two wheel components for the wheels. We group all these elements together, position them based on the initial tile index prop, and turn them based on the direction prop. If the car goes to the left, we rotate it by 180 degrees. When we set rotation in three.js, we have to set the values in radians. And 180 degrees is equivalent to pi, so that's why we have math.pi here. There are also two props that we don't use yet. We don't use the row index and the speed props. We will use them later to implement the car movement and heat detection. Now the only thing that's missing to render the car is the wheel component. To continue with our boxy theme, the wheel component is a simple box with a dark color. Because we never see the cars from under, we don't need to separate the wheels into left and right wheels. We can use one long box that goes below the car, and we can use one for the front wheels and one for the back wheels. With this, you should see a new row appear on the screen with a car. We can define the truck lanes in a similar way. I'm not going to go through everything in detail, but we also define metadata, which is exactly the same as before, except now the type is truck. Then we can extend the row component to map the truck rows into truck lane components. Then we define the truck lane the same way we define the car lane, except this time we are mapping the vehicles into trucks. And we can define a truck component, which is also rendering a couple boxes. You can find the code in the description below. So with this, we can define a map with several rows based on a metadata. Before we move on, for aesthetic reasons, let's add a couple more empty rows before the player to fill the screen. So in the map component, where we added this grass row for the starting row, let's add a couple more with negative indexes, so they will appear before the player. Before we move on with the game logic, let's define the shadows. We are going to define a shadow camera, and we ensure that all the objects in the scene can cast and receive shadows. Let's update our directional light to cast shadows. We need to set up a few more properties to define how. As our directional light has a few more properties now, let's move it to its own component. Here first we have to set the light's cast shadow property to enable shadow casting. We also need to set the shadow map's map size to set the resolution of the shadow map. Higher values will result in sharper shadows. Then we have to define the shadow camera. A shadow camera renders the scene from the perspective of the light to calculate shadows. To define a shadow camera, we need to define the camera frustum. The frustum sets the area of the scene in which the shadows are calculated. In the case of a directional light, the frustum is a box. Shadows are only calculated within this box. Let's take a look at this demo. Here the red dot represents the position of the directional light, and the line going to the player represents its direction. The gray box around the scene represents the camera frustum. The red rectangle shows its intersection with the ground to see what's part of this box and what isn't. Everything inside the box can cast shadows. but everything outside of it won't have any shadow. To define this frustum for a directional light, we need to set how far each side of this box is from the camera position along the different axes from the camera's perspective. So we set how far is the top side of the box, the bottom side of the box, the right side, left side, and also the near and far side of this box. So this is what all these values represent in the directional light component. Now that we have defined the directional light in its own component, let's replace the original directional light in the scene component with this new component. To enable shadows in the scene, we also must set the shadows property in the canvas component. You might think that that's it, but actually, in order to have shadows, we also have to set for each mesh if they can receive or if they can cast shadows. So we have to go through all our 3D objects that we defined so far and set these properties. First, we can set in the grass and the road components that they can receive shadows. We could also set that they can cast shadows, but because they are already on the ground, nothing will receive the shadow from them. Then we go through the player, the tree, the car, and the truck components, and we set both the cast shadow and the receive shadow props for all the meshes. After this, you should be able to see the scene with shadows. Now let's get back to the game logic, and let's animate the vehicles in their lane according to their speed and direction. This is the part where things start to diverge from how would you typically use React. The React way would be to update a state or a prop and let React re-render the whole component. This is fast when working with HTML elements, but it's not very effective when working with 3D objects. We want to avoid re-rendering the whole scene. Instead, we want to update the positions of the underlying objects directly. We only use React to set up the scene and the objects, and then we let threejs do the heavy lifting. React Tree Fiber is just a thin layer on top of threejs, so we can access the underlying threejs objects directly to update the positions of the cars and the trucks. We are going to define a custom hook to animate the vehicles. This hook will need a reference to the 3D object it should manipulate. Before defining this hook, let's get a reference to the threejs group which represents the car. In the car component, we use React's useRef hook to store the reference and bind it to the group element. Then we pass on this reference to the useVehicleAnimation hook, along with the direction and speed of the car. If you define a truck component, then you can also attach a reference to the group element that is containing the truck, and then we use the same hook. Now let's implement the useVehicleAnimation hook. This hook will move the vehicles based on their speed and direction until the end of the lane, and then it will respawn them at the other end. This way, the vehicles will move in an infinite loop. This hook uses the useFrame hook from React Tree Fiber. This hook is similar to setAnimationLoop in threejs. It runs a function on every animation frame. Conveniently, this function receives the time delta, the time that passed since the previous animation frame. We multiply this value by the vehicle's speed to get the distance the car took during this time. We directly update the exposition of the underlying threejs group. If the vehicle reaches the end of the lane, we respawn it at the other end. Note here that the reference passed to the hook might be null, because it's only set after the first render. If the reference is not set yet, we return early from the function. Then the animation will start in the next frame. With this, you should see that the cars and the trucks are moving in their lane. Now let's move on and animate the player. Moving the player on the map is more complex than moving the vehicles. The player can move in all directions, it can bump into trees, get hit by cars, and it shouldn't be able to move outside of the map. In this chapter, we are focusing on two parts. First, we are collecting user input, and then we are executing the movement commands. Player movement is not instant. We need to collect the movement commands into a queue and execute them one by one. So we are going to collect user inputs and put them into a queue. We collect both click events from control buttons on the screen and keyboard events. The player can move in 4 directions. It can move forward, backward, left, and right. We extend our types file to define a new type, move direction, that represents these directions. To track the movement commands, we create a store for the player. The store will keep track of the player's position and movement queue. This store will be a simple file. We are not going to use Zustand yet or any other state management library. The main benefit of using a store like Zustand is that the state inside of it is reactive. If you change a state, then all components that are using the state will re-render. With React Tree Fiber, we try to avoid re-rendering components for performance reasons, and we manipulate the 3D objects directly. For the player, we will proactively get the state from the store in each frame instead of relying on reactivity. So for our purposes, we can simply create a file that exports our state variables and the few functions that manipulate the state. This file will export the state object with the player's current position and the moves queue. The player starts at the middle of the first row, and the moves queue is initially empty. We also export 2 functions. The queueMove function adds a movement command to the end of the moves queue, and the stepCompleted function removes the first movement command from the queue and updates the player's position accordingly. Now let's add a couple controls to the screen. We add 4 buttons to move the player forward, left, backward, and right. Each of these buttons will call the queueMove function from the player store we just defined. This part so far will only collect the move commands into a queue. The actual movement will be implemented in the next section. We also add a new hook called useEventListeners that listen to the keyboard events so that the player can be moved using the arrow keys. In the React component, we wrap the buttons into 2 div elements. We use the outer div to position the controls at the bottom of the screen, and the inner div has a grid layout to show the buttons like this. The forward button spans all 3 columns to make it wider. Now let's also define the useEventListeners hook that listens to the keyboard events and calls the queueMove function of the player store with the corresponding direction. Note that we prevent the arrow keys' default behavior to avoid scrolling the page. Then finally, we add the controls component to the game component. Since the control buttons are not part of the 3D scene, these are just regular HTML elements, we add the new components into a div that will contain both the scene and the controls. We style this new div element to ensure that the game fills the available space. And we also set position relative so that the controls can have an absolute position compared to this container. And while we are not currently using it, now that we write this file, let's also load a font from Google Font and set it as our font family. We will use this font later with the score indicator and the result screen. Now that we have a moves queue array in our player store and we are already collecting move commands, it's time to execute them one by one and animate the player. Let's create a new hook called usePlayerAnimation. Its main goal is to take each move command from the moves queue one by one, calculate the player's progress towards executing a step, and position the player accordingly. This hook animates the player frame by frame. It is also using useFrameHook, just like the useVehicleAnimation hook. This time, however, we use a separate move clock that measures each step individually. We pass on false to the clock's constructor so it doesn't start automatically. The clock starts at the beginning of a step. At each animation frame, first we check if there are any more steps to take, and if there are and we don't currently process a step, then we start the clock. Once the clock is ticking, we animate the player from tile to tile with each step. We use the move clock to calculate the progress between the two tiles. The progress indicator can be between 0 and 1. 0 means the player is at the beginning of the step, and 1 means that it arrived at its new position. At each animation frame, we call the set position and set rotation functions to set the player according to the progress. Once we finish a step, we call the step completed function to update the player's current position in the store, and we also stop the clock. If there are any more move commands in the move queue, the clock will restart in the following animation frame. Now that we know how to calculate the progress for each step, let's look into how to set the player's position and rotation based on it. The player will jump from tile to tile. Let's break this down into two parts: the horizontal and vertical components of the movement. We calculate the player's start and end position based on the current tile and the direction of the move command. Then we use linear interpolation with a utility function provided by three.js to calculate where the player should be based on the progress. For the vertical component of the movement, we use a sine function to make a curved path. The sine function can take an input between 0 and 2 pi. Our progress is a value between 0 and 1. If we multiply the progress by pi, we map the progress value to the first half of a sine wave. The sine function then will return a value between -1 and 1, or in this case, because we are only mapping to the first half of the sine wave, we get a value between 0 and 1. Then to make the jump higher, we multiply this value by 8. So this way, the highest point of the jump in the middle of the step will be at 8. The player also turns into the direction of the move command. We use linear interpolation again to calculate the player's rotation based on the progress. Now it's finally time to update the player component to make use of this new hook. Now that the player can also rotate into its direction, it's also handy to have a visual indicator of the direction of the player is facing. We've wrapped the player into a group element and extend it with a little cap on top of the body of the player. This way, we can see that it's also turning. Then we create a reference with useRef and assign it to this group element. Finally, we pass this reference to the usePlayer animation hook. If we did everything right, the player should be able to move around the game board. The player should move forward, backwards, left and right, and rotate accordingly. However, we haven't added any hit detection so far. The player can move through trees, vehicles, and even go off the game board. In this chapter, we are going to make sure that the player can't take an invalid position. We will check if a move is valid by calculating where it would take the player. If the player would end up outside of the map or on a tile occupied by a tree, we will ignore that move. First, we need to calculate where the player would end up if we made a move. Whenever we add the new move to the queue, we need to calculate where the player would end up if they made all the moves in the move queue and take the current move command. For instance, if the current position is row index 0, tile index 0, and the moves are forward and left, then the final position would be row 1, tile index -1. So we create a utility function called calculateFinalPosition that goes through the moves queue and calculates the final position. Then we create another utility function to calculate whether the player would end up in a valid position after making a series of moves. We use the calculateFinalPosition function we just defined to calculate where the player would end up after a move. Then we check if the player would end up outside of the map or on a tile occupied by a tree. If the move is invalid, we return false. First, we check if the final position is before the starting row, or if the tile number is outside the range of the tiles. Then we check the metadata of the row the player ends up in. Here the index is off by 1 because the row metadata does not include the starting row. If we end up in a forest, we check whether the tile we move to is occupied by a tree. If any of this is true, then we return false. Now finally, let's extend the player's QMove function with the ends-up-in-valid-position function to check if a move is valid. If it returns false, we would return from this function before the move command is added to the queue. So this way, only valid moves are added to the moves queue. Now if you try out the game, you can see that we cannot go backwards from the starting position, we cannot go too far to the left or to the right, and we cannot take the position of a tree. Before we also add hit detection for the vehicles, let's solve another problem. So far we can move around with the player on the map, but the camera still points to the starting position. Let's follow the player with the camera. In this chapter, we attach the camera to the player so that they move in together, and we also adjust how the shadow camera is casting shadows. We can access the camera using the useTree hook from React Tree Fiber. This returns a three.js camera object that we can add to the player group. We already have a reference to the group representing the player. We can attach the camera to the player by adding it as a child to the player group. Because the player reference is undefined on the first render, we need to use the useEffect hook to attach the camera only once the player reference is set. Once we attach the camera to the player, some strange things are happening. The camera is moving together with the player now, but it's also turning whenever the player turns and moving up and down when the player is jumping. This is not exactly what we wanted. We want the camera to follow the player, but we want it to stay level and not jump or turn. To ensure that the camera follows the player but doesn't jump or turn, we've wrapped the player object into another group. The original outer group will be the container that moves horizontally on the map, but it doesn't jump or turn. We attach the camera to this group. Then the new inner group containing the player object won't move horizontally anymore, but it will turn and jump. Let's adjust the player animation to use this new structure. In the utility functions of the usePlayerAnimation hook, we need to adjust how we set the player's position and rotation to work with the new structure. When moving the player along the X and Y axis, we need to move the outer group. But when the player turns or jumps, we need to adjust the inner group. These functions receive the reference to the outer group. We set the X and Y positions as before. Then when we set the position or the rotation along the Z-axis, we set it on the inner group that we can access by accessing the first child of the player object. Now the camera is following the player in a correct way. But as the player moves further away, another strange thing is happening. At one point, the shadows disappear. If we zoom out even more and add the helper box to show the shadow camera's frustum, we see what's happening. We simply ran out of the shadow camera frustum. Here the gray box shows the shadow camera's frustum, and the red rectangle represents its intersection with the ground. Shadows are only calculated within the frustum of the shadow camera, which is statically attached to the directional light. To solve this problem, we need to attach the directional light to the player as well. So first, let's remove it from the scene. Then we can add it to the player in the player component. We add the light within the outer group so that it's following the player, but it doesn't jump or turn with the player. Also make sure to add it as the second element because the usePlayerAnimation hook modifies the first element on jump and turn. Now we almost solved this problem, but if you're moving around, you see that the shadows are changing as we move with the player. The directional light is shining from their position towards a target. And by default, this target is the origin of the coordinate system, the 0, 0, 0 coordinate. This was fine when the light was attached to the scene, but now that it is attached to the player, we also need to adjust the target. Otherwise, the light and the shadows will keep changing direction. To modify the light's target property, we need to have a reference to the underlying three.js object in the player component. We can achieve this by forwarding a ref to the directional light component. Then let's assume that we already set the reference in the directional light component. Once we have this reference, in the useEffect hook, once the references are already set, we set the target of the light to the player group element. Now, how to set the forward reference in the directional light? This is the only part where React 18 and React 19 is different. In React 18, we need to wrap our directional light component with a forward ref to make the forward reference work. In React 19, we don't need a forward ref anymore. We can simply use ref as a prop directly. In either of these cases, once we have this reference, we can attach it to the light. Now that we attached the camera and the light to the player, we should be able to move through infinite lanes while the camera is following the player and the shadows don't disappear. But how do we have infinite lanes? Let's switch from having a static metadata into generating rows dynamically. This way, we can also dynamically extend the map once the player starts to run out of rows. In this chapter, we add utility functions that generate metadata, and we introduce a substance store to manage the rows. Let's create a new utility file to generate metadata. This file we export the generate rows function, which returns the metadata for X amount of rows. It will call the generate row function, which generates the metadata of a single row. It randomly selects a row type, a car, truck, or forest row. It uses a helper function random element to pick a random element from an array. Now let's look into each of these functions and see how to generate metadata for a forest, a car lane, or a truck lane. Let's continue the same file and add the function called generate forest metadata that will return the metadata of a forest row. To generate metadata for a forest, we need to generate an object with the type property set to forest and an array of trees. Each tree has a tile index and a height. We generate 4 trees in a forest. We pick a random tile index for each based on the available range. We use a utility function from three.js to pick a random integer number between the minimum and the maximum tile index. If we just have completely random tile index values, it might happen that some trees take the same position. To avoid overlapping trees, we need to keep track of the occupied tiles in the occupied tiles set. If the generated position is already occupied, we just keep generating a new tile index until we find one that is free. So let's say we picked tile -3 for the first tree, then we mark this tile in the occupied set, and the following trees won't be placed here. For each tree, we also pick a random height from an array. Generating car lanes is very similar. Car lanes also have a direction and a speed. The direction is a Boolean value that sets whether the cars are moving left or right. And the speed property tells us how much distance each car takes in 1 second. We pick a random value for both of these properties with our utility function. Then we need to generate an array of vehicles with the initial tile index and the color properties. We generate 3 cars in a lane. The logic here is similar to generating trees, except that cars are longer. We need to mark 3 tiles as occupied for each vehicle. Generating metadata for the truck lane is the same as generating metadata for the car lane. The only difference is that truck lanes only have 2 trucks, and because the trucks are longer than a car, they occupy more tiles. So after defining our utility functions that can generate metadata, let's use them in a new map store. The map store is a substance store that manages the rows in the game. This time, we need a reactive store because the number of rows is dynamic. As the player moves forward, we will extend the metadata, and we want React to render the new lanes. So let's create a new substance store to manage the map metadata. For now, it has two things. The rows property holds the metadata for all the rows in the game, and the addRows function extends the map. In both cases, we use the generate rows functions that we just defined. As we introduce this store, we can also delete the static metadata we used before. Then, to make use of this store, in the map component, we replace the static metadata with this new store. Because Zustan is reactive, the map component will re-render whenever we add new rows to the store. Now that our metadata file is gone, we also need to replace it in the utility function that checks if a move is valid. We use the metadata to check whether the player would bump into a tree. We can replace the metadata import with the useMapStore hook. Then we can replace the rows variable with useMapStore.getState.rows. This is another way to access the state in the Zustan store. The main difference between this sort of access and the useStore hook is that this way is not reactive. This is useful when we don't need reactivity. Now that we have a dynamic store with a function to extend the map, we can use it to add new rows as the player moves forward. In the player store, we have the stepCompleted function, which is called whenever the player completes a step. This is a good place to evaluate whether we need to add new rows to the game. If the player is running out of rows, we can call the addRows function from the map store. We check if the player is 10 rows away from the end of the current map, and if so, we call the addRows function from the map store. This will create new metadata and trigger the reactivity in the map component to render the new rows. As a result, we have an infinite amount of rows. As the player moves forward, more and more rows are added to the map. Now that we can move forward through infinite amount of rows, let's add the score indicator to keep track of how many rows we have crossed. Let's add our last store called the game store. This is another Zustan store that keeps track of the score and other top-level game states. For now, we only keep track of the score. The store has a score property and an updateScore method that will update the score if the new score is higher than the previous one. Now that we have a store that can keep track of the score, let's display it on the screen. We create a new component, which is a simple React component that reads the score from the store and displays it. This component also comes with CSS to style the score indicator. We are positioning the score in the top left corner of the screen with an absolute position. This element will also use the font we loaded before in the main CSS file. Finally, we need to add the score component to the game component. Since the score indicator is not part of the 3D scene, we add it to the outer div element. And then finally, we can update the score. Once the player completes a step, we call the updateScore method from the game store. We can do this in the last statement of the stepCompleted function of the player store. The updateStore method is smart enough to only update the score if the current row index is higher than the current score. So we can call it after every movement. And finally, we reach the final chapter, when we are going to implement hit detection and we add a result screen where we have a button to restart the game. We are going to add a new hook that checks from the vehicle's perspective if they hit the player. If so, we will change the game status to over. So let's extend our game store with a new property status. By default, this value will be running. And we also add a new method called endGame, which will set the status to over. We call this method when the player gets hit by a vehicle. So far, the player and the vehicles have handled their movement independently. They have no notion of each other. To handle hit detection, either the player needs to know about the vehicles or the vehicles need to know about the player. We choose the former approach because this way we only need to store a reference to the player in the store, and all the vehicles can check against this reference. Let's extend the player store with the ref property to store the player object's reference. We also expose a setRef method that sets this reference. Then we can call the setRef method in the player component to set the reference in the store. We already have a player reference, so we can pass it to this new setRef method in the useEffect hook once it is set. Then let's define the hook to handle hit detection. We check if the player intersects with any of the vehicles. If they do, we set the game status to over. This hook is from the perspective of a vehicle. We will add it to the vehicles. It receives the vehicle reference and the row index. We check if the vehicle intersects with the player if the player is in the same row, or the row before, or the row after the vehicle. We use the useFrame hook to run the hit detection logic on every frame. We calculate a bounding box for the player and the vehicle to check for intersection. This might be an overkill as the shape of our object is known, but it's a nice generic way to handle hit detection. If the bounding boxes intersect, we call the endGame function from the game store. Then we can call this hook in the vehicle components. First, we add it to the car component. We pass the car reference and the row index to the useHitDetection hook. Then we do the same in the truck component. If either a car or a truck hits the player, the game changes its status to over. You can add further logic, for instance, to disable further movement of the player. We don't cover this here, but you can add it as an exercise. Instead of covering that, let's display a result screen with a final score. So if the game is over, we can display a pop-up with the final score and the reset button. Once the player gets hit by a vehicle, the game status is set to over. We show a result screen with the final score and the button to restart the game. Let's add a new component called result. This regular React component reads the game state from the store and displays the results if the game is over. It also has a button to restart the game. In the next section, we add the necessary logic to reset the game. The result component also has a style. We style the result as a centered container with a white background and a red button to restart the game. Finally, let's add the new component to the root of the game. With that, only one piece is missing to complete the game: the logic to reset the game. The result screen is shown when the player gets hit by a vehicle. There, if the player clicks the retry button, we call the reset method of the game store. Let's implement this method. The reset method resets the game to running status, sets the score to 0, and calls the other two stores to reset themselves. To reset the map store, we expose a reset method that generates new rows and sets them as the current map. We use the same generateRows function that we use to initialize the rows and to extend the rows. Calling this method will reactively re-render the map. And finally, we need to reset the player store. The reset method returns the player to the starting position and clears the moves queue. This function resets the metadata and the player object's position and rotation in the scene. With this, you have a fully functioning game. Congratulations, you reached the end of this tutorial. Of course, the game is far from perfect. You can always extend with new row types, new design, and new logic. If you haven't checked it before, also check out the same game with three.js and vanilla JavaScript, and check out my other game tutorials. You can find the source code and a lot of interactive demos of this game on my website called JavaScript Game Tutorials. It's a free site and it's a lot of fun, so go for javascriptgametutorials.com. See you at the next one.